Hi guys, Matt from Howtech here, and we're doing another workshop feature here in Lake Havasu, Arizona, in the United States of America. Today we're at EFI University. We're going to go and speak to Ben Strader, see if we can extract some free knowledge for you guys. Ben Strader, EFI University.
Thanks for coming, buddy. Yeah, I'm doing good. How are you?
Good, good. Thanks for having me.
You're welcome. You're welcome.
So tell me, where are we? What do we have here?
Well, as you first walk into school, this is kind of where the classroom starts. So every one of our training courses, no matter what it is, always starts here. So we make sure we cover all the fundamentals before we get our hands dirty and start working on stuff. So that's what we're doing here.
Now, before we move on, I've got to ask, what is this? This is the world's smallest chassis dyno. Is this dyno for midgets?
Yeah, basically what we do is we get all the students on there and see who can run and produce the most power. You know. It's,
okay. Yeah.
No, actually, that in the old days when Mainline was a relatively small company, they used to take that to like the PRI, SEMA trade shows, and it was their display.
Okay.
And so now that they bring full-size ones everywhere, it was just sort of languishing in the back of their shop. I was over in Australia a couple of years ago, and Todd said, hey, you know what? This would be cool. Do you have daughters who drag race, and they have junior dragsters? Maybe we could build a dyno for junior dragsters.
So this thing works?
It's a real dyno. Yeah, it has an actual eddy current brake in it, and it's like a steady-state load-bearing junior dragster dyno.
How much horsepower does it read?
Allegedly over 100, somewhere close to 200. I'm not really sure because we never really tried to max it out, but it's pretty darn cool.
It's a dyno for Miatas.
Exactly.
And tell us a little bit about EFI University and how you guys came to be, where you came from and where you are now.
Sure. Okay. Well, started the company back in 2003, 15 years ago. And it just kind of started out of a need, like a lot of businesses do. You know, I had a performance and racing shop, did dyno stuff. We sort of specialized in EFI. And most of my kind of friends or associates were engine builders. And so I noticed that most of the engine builders were pretty good at building engines and making power, but they just really didn't know that much about tuning, specifically on the EFI side. So actually, I just started out with a weekend seminar that I'd kind of written notes on the back of a paper, and I really didn't think anyone would care. I just kind of did it for a few friends, and I put it together and thought, I'll just do this once, and then that'll be it, you know. But I was wrong about that. It turned out that there was a real need in the industry. And so I kind of started out back in 2003 just doing seminars, a couple here, a couple there, and I would get more requests. And so after probably 6 months or 8 months or a year of doing that, I realized, wow, this could be a real thing. And so I, quit my day job, as it were, and pretty much closed up the performance shop to just do EFI training full time.
Now, you also have a book. That's about the same time you
It was
did the book?
almost exactly the same time. Actually, I'd written this book called Building and Tuning High-Performance Fuel Injection Systems, Electronic Fuel Injection Systems. And I wrote the book about 2002, but it didn't really get published until 2003, which is the same time I started doing seminars. And so it actually probably had something to do with my success in that, I guess because I had written a book, I kind of became the de facto guru or whatever, as undeserved as that reputation might have seemed. It was good for my business at that time, so I just kind of took advantage of it.
Now, this is something that really interests me. You've got a whole bunch of engine components going on here.
Yep.
What do we got here, and how do you guys kind of use that?
Well, okay, this is probably my favorite room of the shop, too, because I spend the most time in here. But this particular engine that's in front of us, we use for a course that we call Competition Engine Development. Now, it's a pretty sophisticated course that's not really about how to build engines and more about how do I take an engine platform, evaluate where the shortcomings are, and figure out how to make them better. So we teach how to document that progress, how to go back and revisit why you made certain changes, but it's a very mathematical and scientifically based approach rather than let's just change parts and run them and see how they go.
Can you give us some tips? What are the sorts of things that we might be looking at in this engine?
Sure, I'm glad to share as much as you guys will listen, but one of the reasons that we do this configuration of engines, it doesn't matter if it's Hondas or Mitsubishis or whatever, but the LS platform is obviously pretty ubiquitous and are all over the place. And so for me, I wanted to use a platform that was commonly seen and understood. That was the first thing that was important. And I based the entire program in it so that as we have multiple engines here, we have parts inventory that's common. So really hard to go, well, today we're going to do a Ford and next we're going to do a Chrysler. You'd never have enough parts, So that's the only, I don't have any special admiration of LSs that somebody else doesn't have. It's just a good platform. That being said, what we wanted to do is take a platform like this that also had some shortcomings and figure out ways to make them better.
Sure.
So we specifically and purposely chose a high RPM. By that I mean 9,000 RPM and above. High compression, and by that I mean 15 to 1 and above. We've been as high as 17.5 to 1 in our testing. And naturally aspirated only. And the reason that I do it naturally aspirated is because it's hard.
Okay.
Anybody can bolt a turbo on and make a bunch of power on a stock bottom N53, in which case there's no point in having a class about it.
Sure.
So some of the stuff that we go into is very technical and very in-depth on what it takes to do the development work on a competition or racing engine, including obviously machining tolerances and clearances and things like that that you would expect in a class like this, but a whole bunch of stuff that you wouldn't expect, like valve train geometry and understanding kinetic versus potential energy that's stored in the valve train system, and how to plan an engine project from scratch and say, my goal is I want to make, pick a number, I want to make 700 horsepower, and then we go through and identify what the limitations are and what the constrictions and restraints are, and then come up with a way to meet that goal. And also, more importantly, help guys understand, well, is that goal achievable? Before we start spending money and buying parts, if it's impossible to reach that goal, we need to change the goal or change the plan. So a lot of this class is based on that kind of stuff.
Where are you now, and what do you provide these days at EFI University?
So yeah, that was a long time ago, and I would say the company's dramatically different now than it was back then, and probably has changed a lot along the way too, from what I imagined it was going to be to what I wanted it to be to what it became, have been different. But what I would describe us as now today is like a vocational school that's targeted towards motorsports and performance markets, and kind of more than just, I sort of probably used the term EFI University the wrong way back 15 years ago, because it's become more of an engine and motorsports, sort of facility. But what I like to describe it as is we are professionally focused and a la carte. So what I mean by that is our courses are primarily designed for people who are already working in the field or who want to work in the field at a professional level. And they're short-term and very narrowly focused, so that the idea is that somebody could come to our school for 2 days, 3 days, or a week and get highly focused education on fuel injection, turbocharging, engine development work, or anything to do with performance and sort of motorsports-based stuff, and then go back to work and use it. See, traditionally, a motorsports kind of based school would be 16, 18, 24 months long. Well, the problem with that model that I've found is that adults who have wives or girlfriends and car payments and apartments, they can't afford the time commitment, even if they could afford the dollars commitment. So we've kind of developed a strategy that works well for us. It's different than what everybody else has. But basically, we offer a lot of engine and EFI and motorsports-based training in short, small bite-sized classes that a guy can come and take one of them or all of them together, get what they need, and then get right back to work.
All right, Ben, so I want to talk about pistons and piston rings. You've got a whole bunch of machines here.
Sure.
To help measure things. Give us a knowledge bomb on pistons.
All right, I'll throw a couple at you here. There's obviously weeks and months of stuff we could talk about, but obviously in the process of developing our engine, we keep changing the shape of our piston, both on the crown for compression ratio and the actual shape between the relationship of the top of the piston and the skirts and stuff like that. And the reason is that for us, because it's a naturally aspirated engine, we only get so much airflow. We can't turn up the boost, can't add nitrous. Sure. So oftentimes once we've maxed out that capacity, what we have to do is try to find other ways to get power out of the engine, like not lose as much. Sure. So friction and drag become a big deal. So I'll start with rings and talk to you a little bit about piston rings.
Okay.
The rings that we run in this type of application are mind-blowingly small for most people.
I see one right here.
Yeah,
this little guy here.
Yep, here, I'll take the package and you can hold the ring. These are made by Total Seal piston rings out of Phoenix down there. This particular ring that goes in the engine, this is 27 thousandths of an inch thick. That's our top ring.
Right, so this is one that really takes all the punishment,
right?
Yeah,
absolutely, yeah.
And it's 27 thou.
That's thick, and it's only 103 thou on the radial, or how wide it is. So our ring groove depth is pretty important then to support that ring. But the thing is, all of the radial tension that comes from the ring, the part that pushes against the wall, is, that's spring loaded. Well, that comes from the radial dimension of the ring. That's this dimension here, not the thick. And so as we shrink that radial, we have way less mechanical tension available to seal the cylinder.
Pushing out.
Right. So we have to modify the piston. We drill these holes that are in the top that go down behind the ring into the groove and allow the compression and the combustion gases to get behind the ring and push it out against the cylinder wall.
Okay, so you're actually using cylinder pressure, combustion pressure, to create the seal behind the ring.
Yeah, without that, there would be almost no ring seal because the mechanical tension of the ring just isn't there.
Because it's so small, so thin.
Yeah, exactly. It just doesn't have the, think of a big heavy spring in your car versus like a little lightweight spring in your watch. It can't provide the same load and force. So so ring choice and ring design becomes a critical point.
So I guess also that reduces your losses for the cylinders that are not on the combustion stroke.
Absolutely.
Because you're not pushing all that pressure against you and don't have all that loss against the
That's
the wall of the
exactly
cylinder.
right. And so because of that lower friction, that's power that we had to make in the cylinder that we had to give away to friction before that we
Right.
get back. So we're not necessarily making more power, we're just saving more of it for the crankshaft.
So there's a custom piston that does that, or will any piston do this?
Basically, it takes a custom piston. There are some rare examples where you could basically put spacers in a piston that had a big ring groove and
Yeah.
you could shrink it up, but it's not ideal.
Okay.
So yeah, it basically takes a custom piston.
That is magic.
Yeah, it's pretty cool.
Yeah.
So obviously, when we do that, the ring's ability to seal in the cylinder, combustion chamber, whatever, is important. And so we spend a lot of time prepping the cylinder walls, which I'll be happy to share with you a little later. But one of the things I want to point out is after we get the cylinder walls prepped, they're so precise and they're so delicate that we have to be careful with them, so much so that we don't even use the block to set the end gap of our rings.
So talking a little bit end gap, that's a bit of a thing on
Definitely
the
one of those.
internet.
Yeah, one of those things. Some guys get extremely carried away with it. I care about it, but it's not like, oh my gosh, I can't run the engine if it's too thou different or whatever. The general idea for guys is that you need enough gap so that when this gets hot and it grows together, they don't butt together.
Yeah, because as it expands, it actually closes in.
Up,
Yeah.
right? Because it can't. The cylinder wall doesn't get bigger, so
Right.
it just keeps creeping
I
along.
hope the cylinder wall doesn't get bigger.
That's right. Yeah. The problem is if you make the gap too big, now we have an escape path for the gases to
Push
get
down
out,
through.
and that's just lost energy we could have used to push the piston down. So, depending on the application, is it naturally aspirated, is it forced induction, nitrous, whatever, and how big is the ring, how much will they grow? So we have to adjust that. But in order to set it, traditionally what guys would do is they'd set them in the cylinder bore and they'd square them up and they'd put a feeler gauge in there. Well, as you're doing that, you're actually scratching and scraping on your finely
Right at the
produced
top of the bore. Yeah,
right where
yeah.
all the compression and cylinder pressure is going to be. If you think about it, when I'm in the power stroke of the engine, I'm not at bottom of the center, I'm way up near the top.
Yeah.
So the part that matters the most is that first, inch or so
Sure.
of cylinder treble, which is
Yeah.
exactly where guys set their ring gaps.
Got it.
So we actually spent a fair amount of money to buy these things called ring gauges.
Okay.
And the fact that it's called a ring gauge doesn't have anything to do with a piston ring, but it is a precision honed machine
Okay.
piece that you buy from outside companies
Yeah.
that get used for all kinds of stuff in all different industries, like go, no-go gauges.
Yep.
This happens to be a 4.185 dimension, which is exactly the same as our cylinder bore.
Sure, yep.
And it has an X dimension, which means it's typically guaranteed to 4/100,000ths of an inch in accuracy.
Okay.
So typically what we'll use it first for is to set our dial war gauge so we can check our cylinder sizes.
Yep.
And that gives us an accurate place. Then once we've done that, now we can actually use that hole to put our rings in there.
Then you set the end gap.
Then we set our gap, and then we know they're good for the engine. So that way we don't tear up our new honing job that we put all this effort into while we're setting end gaps.
Knowledge bomb. With such a breadth of and depth of knowledge, both in the engine and the tuning and the whole motorsport department, can you give us a little bit of a, maybe a bit, not a horror story, but what's the most difficult engine that you've ever had to tune?
So obviously there's a million that come to mind. I don't know if I could pick exactly one, but I probably have two that I would share with you.
Okay, share two.
The probably the most challenging from a physical tuning standpoint was when there was a guy named Daryl Greenemeyer who raced aircraft at the Reno Air Races. And what made that challenging is it wasn't really a special engine. It was turbocharged, it was horizontally opposed air cooled, all those things. But what made it hard is I couldn't be in the vehicle. He was literally flying around and I'm using radio telemetry to send data back and forth between the ECU and the thing. And the pressure was like, if you screw up and hit the wrong button, he can't pull over. Like he comes crashing out of the sky. That was very challenging.
Fairly high stakes.
Yeah,
When the
exactly.
vehicle falls out of the sky and everyone burns.
It's
to
one thing when
fiery
you
death.
could blow up an engine. It's another thing when you could kill somebody or yourself or whatever. It's a totally different level of responsibility.
Yeah.
So,
Yep.
and then, more recently than that, back in 2016, I got the opportunity to work for a bunch of NHRA Pro Stock teams.
Okay.
And what was cool was that when I went into it, they were pretty convinced that their engines were very special, and they are. However, they're not necessarily a different animal. It's still just an air pump. And so I took that approach. The main difference was things that nobody else cared about, they looked at under a microscope. And so there were times when between 2 rounds of racing, I might have to adjust 40 different tables. And so we would have gear-based corrections and cylinder-based corrections. So you got 8 cylinders, you got 5 gears. So that's actually 40 fuel tables and 40 ignition tables for corrections. And we would go sit down as a crew and go through the data and go, it's lean at the top of second gear, but then it gets rich at the bottom of third gear or whatever. And like the amount of time that was available for me to do that was very high pressure and very high stakes, not a lot of room for error there either, so a lot on the line. So I would say those are the ones that stand out the most for me.
So from a tuning perspective, you're making changes individually on each cylinder based on data that you've captured during a run.
Absolutely. So we would have an O2 sensor in every cylinder. We'd have G-meter, we'd have data loggers and all sorts of different stuff. And you'd try to make your best guess at how the engine was going to behave. But the problem was, like, the crew chief might make a change to the clutch and the car would accelerate harder, and so fuel moves differently in the manifold, and now the cylinder you thought was going to be rich is lean, and vice versa. It would happen all the time. So very challenging environment to work in.
All right, Ben, what have we got on the engine dyno here?
So this is one of our our test mules. A lot of people like to use that term, but this is pretty much a junkyard stock, if you will. I mean, we kind of just freshened up, but it's a totally stock 5.3, stock bottom end.
And do you use this for the engine building course?
No.
Okay.
This is a completely different course altogether. This is our advanced turbo concepts course.
Okay.
And it has nothing to do with building engines. It has nothing to do with tuning engines, maybe just a tiny bit, But ultimately, this course is about understanding how turbocharged engines behave in different scenarios. So
okay.
A lot of this course is focused on what data should we be looking at, how to collect that data, and how to interpret it.
Okay.
And so what we do is we run the engine with turbocharging under various levels of boost. We might decide to change a turbine housing or something about the physical layout of the system, and then rerun it under similar conditions, collect new data, and then be able to plot that across, say, a compressor map, or pull a data log out of our ECU or something like that.
So you got the Haltech Elite 2500.
We do. Yeah.
What do you use that for on this engine? Obviously, it runs the engine.
Yeah, I mean, and that's true. Obviously, we could run a lot of different ECUs, but the Haltech specifically has a couple of features that we use specifically for a turbocharged engine that allows me to teach the class and make hardware configuration changes quickly, but not have to do much retuning. And so specifically with respect to the pressure ratio across the engine with back pressure and boost and all the wastegate position, because the Elite was one of the few that allows us to kind of roll all those into the program, we decided that was a good choice because we could eliminate that part and focus on what is the turbocharger doing instead of, okay, did that change happen because we changed the boost, or did it happen because now our tune-up's way different or whatever? So the Elite helped us kind of achieve that.
So on the software setup there, are you using the engine pressure ratio as the load source?
That is how we do it, yeah.
Okay.
So the biggest differentiation is most people that are currently probably using that are using it as some form of barometric pressure versus boost.
Yeah.
Whereas we use the comparison between the exhaust pressure and the boost pressure, but it's the same idea. We use the engine pressure ratio feature exactly for that reason.
Yes, so to give you an idea of what that means, on the fuel map, the load axis is actually pressure ratio, so the difference of pressure from the intake to the exhaust. And so obviously you're running an intake pressure sensor and an exhaust pressure sensor to get that information.
Yeah, and the way that I describe it to my students is we think about it like, you go to the dentist and you floss your teeth with that little piece of string. And I always say, well, imagine if you took a piece of string and you fished it all the way through the inlet and down the thing and out the exhaust pipe, you could grab both ends of your string and you could floss the engine. So if you think about that in terms of pressure ratio, I have exhaust pressure on this side and intake pressure on this side, and they fight each other.
Yeah.
So obviously, whichever one has the biggest pressure, the air is going to move that direction, and it determines how much. And so we can effectively use the engine pressure ratio function in the ECU to sort of, I hate to use the term self-map, but essentially model what's going to happen to the engine before it actually happens.
Which makes perfect sense, because if you think of what volumetric efficiency is, it's the actual amount of air that passes through the engine versus its theoretical capacity.
That's right.
So if you have pressure on the intake and pressure on the exhaust, well, pressure on the exhaust is stopping air going out of the engine. Mm-hmm. So for the next engine cycle, it can't get out, so more can't get in to replace it.
That's exactly right.
Just like if you've got more pressure on the intake pushing air in, then more goes in.
100%. So we teach that in the class. We teach that in our tuning classes. That's a concept that flows through all of our classes, but especially the advanced turbo class. And so it's really helpful to have an ECU that we can do it with. There's lots of ECUs that would run the engine, and we debated about that. We thought, look, I could just have 5 different calibrations and plug a new one in every time, but then there's always that question of well, did he give it the super good tune-up on this one?
Sure.
And so we just said, look, if we eliminate that variable and the thing just fixes itself, well, then we can focus on what the turbo is doing. And so the cool thing about this class is not only to learn all that turbo stuff, but you also learn about how to make an ECU do all the hard work for you. Tuning is some kind of black magic, and that you just have to be good or you have to be lucky at it. This is what we refer to as the machine of sorrow. When it comes to cylinder bore preparation, we've learned a ton, but we're still learning as we go, and our preparation keeps getting better and better.
What's the most dangerous mistake that people can make when tuning an engine?
Oh, let me just try throwing fuel at it or leaning it out or try some more timing because you make a mistake that you didn't even know you're making.